Okay, hello everyone to BCAM Topology seminar. Today, Chung-Ping Lai is going to tell us about persistent homology and discrete Morse theory. So this is a follow-up to his talk from last week.
Yeah. Thank you everyone for joining. So this is basically this is the second. So this is like a follow-up to the talk previous week. I will try to like make it so that the talk is like a bit self-contained, but I will gloss over some ideas that we discussed like more deeply last week. So basically, this persistent homology, this is like a central tool in like topological data analysis. And as a basic idea, like the computation difficulty scales with the number of cells. So for that reason, we will see if we want to just and as we discussed like last week, like discrete Morse theory is like one way to reduce the number of cells, right? So that's why it makes sense to see if you can use discrete Morse theory to reduce this complex. So persistent homology. So this is the overview. And yeah. So firstly, I think I will so firstly I would just want to briefly explain what persistent homology is at all. I've heard that a lot of you have already have exposure to the idea. So it will be less math, but I think I still want to give like at least an overall picture of like what this is about. So at a very basic level, persistent now we can like see 8 points on the screen on the slide. At a very basic level, we can intuit. So like at our intuitive, like if we look at like these points like intuitively, then we can roughly tell this is a lot of you probably will agree with me when I say, oh, this 8 points forms a circle. But how do we quantify? And this is what happens if you have point clouds, which are some points like in data set. So if we can like human can tell that these points probably form some kind of circle. But how do we like have a rigorous mathematical framework to say that? And that this is like more or less what persistent homology offers. Okay, so quickly go through the definitions because this is a follow-up to the talk last week. So we want to use the framework, which is an abstract cell complex. And abstract cell complex basically means we basically grade the dimension, grade the different cells by their dimension. And then instead of defining phase relations, we have this boundary incidence function B, which 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 represents the relation between different cells using like their boundary incidence. And simplicial complex, which will be the main object of when we discuss persistent homology, is is something that we can realize as an abstract cell complex. And the boundary incidence will mostly be 1 or -1, depending on how we orient the thing. And then for an abstract cell complex, it has an associated chain complex, which much like a lot of the combinatorial spaces out there. So we can compute homology, etc. And in the case when the original complex is a simplicial complex, well then this associate chain complex of the cell complex will actually just be the simplicial chain complex. So it will so we change our framework from simplicial complex to abstract cell complex, but really we haven't changed a lot of things. So that's the idea I want to sell. Now, next, how do we move it further? Next, we have this idea called filtration, which a filtration is a sequence of cell complexes, and then so we use like a superscript P to denote which of them is, and then we want the sequence to be a nested sequence in the sense that like every complex is a subcomplex of the next. So we have xp minus 1, xp subset xp subset xp plus 1. And importantly, because the boundary, even though we have like increasing number of cells, if we like go up the sequence, we can actually use like a single boundary function to a single boundary incidence function for all the complexes. So that's how this filtration works. And to just and if we realize this in terms of like chain maps, like in terms of if we look at like the chain associated chain complexes of each of the cell complex in between, then we can derive these like inclusion chain maps, because all the associated chains, the bases are just the bases are the basis of the diff chain group is the dimension D cells. So this we have like an inclusion relation, and we can include from P to P plus 1, but we can also include from P to P prime. So we are like skipping over a lot of we can like skip over a lot of the intermediate cell complexes. And also I almost forgot. So for each cell complex in this sequence, we call it a frame. So like XP is a frame, XP minus 1 is a frame of the filtration. And the other thing we sometimes do is like we just look at the union of the entire filtration. Then we have like a single we have a single cell complex. And sometimes we look at things that way as well. And notably, if we have a single cell complex like that, the boundary incidence function is we still have the same boundary incidence function, and the boundary incidence function at each frame is just like a restriction. So how does that relate to our original premise of like a persistent homology, right? The two of persistent homology. So this is where I'm going to be slightly to skip over some steps, but I still hope to like just tell the story of this persistent homology. So firstly, uh, the way we think about persistent, so the way we say we realize the shapes that may exist like on a point cloud, which is all, in other words, a lot of vertices, is we use those data points as a center, and then we draw an open ball on it. So but of course, but then we have the problem. So what is the size of the open ball we want to what is the size of the open ball that we want to use, right? Because that is very arbitrary, and really case by case. Turns out we can use every size. So we can like look at different. I mean, we can first look at like what different sizes of the open ball gives us, right? So here we have like a sequence of like different radius. So for the K1, we just have the vertices. We choose the radius of the open ball to be 0. Then we just have a lot of vertices. For K2, we start having like some radius, but the radius is really small. So we just have like a lot of disjoint open ball. Whereas on K3, now we choose a larger radius. And we start seeing the open ball to be intersecting. And we can sort of see there are like some kinetic components, so which shows some vertices are closer to the others. But it's still a lot of like just disjoint component. K4 is probably the most interesting one because now we see the open balls joining together to form a ring. And this seems to be the ring that we intuitively see if we look at K1, which is just the vertices. And K5 is like we increase the ring further and that we will increase the radius further. And now we see, and we still see a ring here. Um, but notably, so this is there's yeah, but if you try to imagine the radius to increase even further, then you may start seeing that we have like giant open balls, and that turns out that we just have like a lot of open balls intersecting, and that really goes the other way back in the sense that now we have like less information, like the whole disappear because the open balls are too large. So obviously, no, okay, I shouldn't say obviously ever, but here the radius for K4 and K5 seems to be the best radius in terms of showing what is in terms of like making the ring show. But in practice, like when we choose an arbitrary data set, we really can't decide what this R is. And the idea of persistent homology is actually you don't have to make a choice. You can really think about every different value of R. Um, so but okay, we can leave that further. We can leave that behind for a bit. But basically for every R, you have like a lot of open balls and you intersect to form different shapes. And my claim here is because we just came from abstract cycle complexes, or in other words, simplicial complexes. I think the goal we first want to like construct a simplicial complex that represents that. So here, this is the part where I'm going to be a bit hand wavy, and just go through some of the rough idea of the mathematical justification for the definition that will be coming. So the first step, we look at the union of open ball and at a particular radius r. And what I'm going to the assumption that I'm going to make is that all the open balls that I just constructed, they form an open cover of like some hidden manifold, which is in other words some manifold which contains that some because we try to think about like all the data points to be belonging to a certain manifold, and that when we are using these open balls, we are like making the assumption that these open balls form an open cover of the manifold that are being hidden, and in turn that reveals that makes it possible for us to like study the manifold. Um, and then once you have like a lot of this open ball, the next tool you want to use is like the check complex, which is the check nerve of the open cover. So in other words, once we have chosen a radius, and we have like a lot of open ball, if we assume it to be like an open cover, we can construct the check nerve of the open cover, which is like a simplicial complex, which we call the check complex. But turn out, unfortunately, the check complex, this CRX, they are really difficult to compute. So instead, what happens is people use the Vias-Torres-Rips complex to approximate this check complex. And the reason this is like maybe a good approximation is we have like this relation where basically because as I accidentally hinted earlier, we are not looking at a single radius, we are looking at every radius possible. So the fact that the Vias-Torres-Rips complex is really in between some different radius of the check complex makes it a good approximation. And I think this 2R bound can be is not strict. So I think it is possible to like cut down the bound further. So let me quickly define this vs torus Rips complex. So let X be a metric space. So interestingly, this okay. Let me go through the definition first. So let X be a metric space, and then we choose a value R radius from 0 to infinity. Really, then we have this vs torus Rips complex. Is a simplicial complex where we define where the set of vertices is X, and then the set of simplices, I use VRRX here, is the subsets, finite subsets of X, such that the diameter of S is less than or equal to R. So which means like the further you can go. So finite subset such that the furthest you can go is less than or equal to R. And yeah, it's less than or equal to R. And we take the empty set out because and we take the empty set out. So this is and then the interesting tangent, it's like a tangent, but it's interesting is this metric space, even though when we talk about point clouds, etc., we are always talking about finite discrete metric spaces. You can actually use like some continuous metric space, like a circle, etc. And it's like a topic that is like being explored by some other people in the field. So what if we don't use the finite metric space? What if we use some infinite or uncountably infinite metric space, like an S1? So what happens to the Weierstrass Rift complex? Which is like an interesting problem, but like it's an interesting tangent. Let me put it this way. So this is now we have and the claim here is that because we just defined filtration. So filtration was as we defined filtration to be a lot of simplicial a sequence of simplicial complex with the subcomplex relation. This Weierstrass Rift complex, the filtration that we are going, this Weierstrass Rift complex is the filtration we obtain from the point cloud, the way the filtration works is that as you increase R, there will be more simplices. Like Rx will contain more simplices as the value of R increases, because you are like increasing the diameter. So you are like allowing more finite subsets to join. So that's like how you have like a filtration. And so now so this should unite the definition of the filtration, which is why we care about filtration, essentially, if we care about persistent homology. So now I'm just going to, and now we can, so now we have a filtration, and we obtain this filtration from a point cloud. So the filtration is a filtration called the Weierstrass Rips complex that is well motivated. So now what do we want to do with it? And the answer is persistent homology. So what is persistent homology? So let me first show the really nice, the best presentation of persistent homology, I think, which is like a barcode. So what is a persistent homology? So if we look at this this barcode is if we look at a lot of images here. So the good thing about working in a field with a lot of computation is there are a lot of great images out there circulating, which shows the topic. So there are like 7 images here, and this is really constructing the Weierstrass Rips complex of the same set of underlying vertices. So when you move from left to right, you basically you are basically increasing the radius r. It's like you are constructing the Weierstrass Rips complex, except you are with like increasing radius. So that's why so now you have the same set of vertices, but as you move from left to right, you contain more and more simplexes, especially the higher dimension simplex, um, because of like finite subset with radius bounded above, right? So that's what they are. And if we look at the H0, so here we look at the zero homology and the first homology of the resulting simplicial complexes. If we look at the first image, because the radius, okay, here this is using epsilon, but sometimes people use, so these images use epsilon, but it's the same as r, radius r, as I previously mentioned, as I previously discussed. So at the first image, because the radius or the epsilon is still really small, so there are not a lot of connectedness between different vertices. And we definitely do not have a cycle. That's why the H1 is completely, so what we want to look at is, when we look at this, is we want to look at, so for the cycles, we want to look at this section. We see there are nothing here. That means there are no H1 cycle here. But there are many, the bars intersect this dotted line in many places. And what this means is that there are a lot of H0 components. There are a lot of like H0 components at this frame. So next, we look at the H1, or like we look at like a later frame. So we look at this frame. So now we have two cycles. We have two cycles here. We have a square here, and then we have a hexagon here. And the way we read the barcode is that we draw a dotted line downward, and we see that there are two bars intersecting this dotted line, which means at this frame there are two H1 feature. And if we look at instead of looking at the H1 feature, if we look at the H0 feature, then we are looking at this portion of the barcode. And here we have less bars intersecting the dotted lines, because as the R increases, there are like more connectivity between the vertices, and different vertices merge into the same component. So there are less intersections, but there are still a lot of intersections. And next, we want to look at let's look at another frame. We can look at this frame. I mean, yeah, we can look at this frame. Now there are like three H1 components. So which is we have this square, we have a square here, and then we have a hexagon here, and then we have another quad, like I forgot, fourgon, I guess, fourgon here. So we have like three cycles. So the H1 looks like this. And now every vertex is like fully connected. So if we look at the H0 component of this ring, we only have one bar left, because all the vertices are being connected. And then we can see that like as the radius increases, there are like more connectivity. And at the very end, let's look at two more frames. So if we look at this frame, so now the like all the vertices are connected. So there's like one H0 component left, and there's like also a big square here, that is like not being merged. So that's something. And if we look at the final frame, so that's an interesting thing. But if we look at the final frame, Then with the radius is really large, so everything is like fully connected. So we just have like one H0 component, and all the H1 components are also gone. Okay, so that's and why do we want to present things like this? The good thing is because if we look at individual R, we get really different we get really different information about the cycles. But the insight of like doing things like this way is that instead of looking at individual values of R or in individual values of R, we can having a chart like this allow us to look at all the values of R at the same time. So the claim is if a certain homological feature persists a very long time, which is where the name comes from, then we may be tempted to say that this feature is like more significant. So for example, this like H1 has like this bar. If we look at this bar, this bar really corresponds to this particular H1 feature, this particular hole here. And because this hole exists for quite some time, so we'll be more inclined to say this hole is perhaps a more important hole for this point cloud. And the other the other feature that persists a long time is like this bar here. So this bar here, which is, and if we look at what it corresponds to, it really corresponds to this hexagon. So it takes more time. So this hexagon exists like among the frames that we look at. We have among the frames that we drawn out. This hexagon like exists for like this hexagon cycle exists for like 3 frames. So we are tempted to also say this is probably a more significant feature of the hexagon. And so we have this. So that's the idea of why this seems to be makes a. So I hope here what I'm doing here convinces you that this is like a good way to look for cycles if you are just given a lot of point clouds and their pairwise distance. So like or in other words, a metric space, and that's how you at least this like you can like sensibly explain there may be some features of interest here when there are really less method, at least as far as I know, that who can show these cycles. So what's the math about this? So here I'm going to, so the math here will be handled slightly different. Will be handled, okay, how to say it? So the math part is the way we get this, all this thing here is we compute a persistent homology group. Well, we are not computing the persistent homology group exactly, but it will say an equal because we define this because this is the thing that we will try to compute. And if we have this definition, we can recreate the original barcode. So what is this like persistent homology groups? So essentially, so first we look at the dimension. We look at the D dimension, just like homology group, we have to specify what is the dimension of the feature we are looking at. Then we look at 2 different values, P and P prime, and we say the homology group that persists from P to P prime is this. We have like this formula here, but something that is perhaps a bit easier to memorize would be the formula at the bottom. Alternatively, is instead of looking at like some really weird divide instead of doing a lot of algebra in a topology seminar, so we can just look at 2 homology groups, which is first is the the deep homology group of the P frame. And then we just look at how this homology group is being included with the inclusion map. So the ID P to P prime map. So this becomes a subgroup of the deep homology group of the P prime frame. So I should write out here. So this is no, this is, so this is H D X P prime. So this is, okay, my writing is not great. So X P prime. And you have to take my word for it a bit. If you have figured out all these persistent homology groups, you can basically recreate the barcode that we have seen earlier. So we have these persistent homology groups that we want to compute. So okay, so now now I discussed persistent homology and I motivated the thing I want to compute. So what do we want to do with it? Well, now it's time for the discrete Morse theory to come in. So again, a quick review of like the discrete Morse theory, the topics in discrete Morse theory we discussed last week. So I'm going to ignore the discrete Morse function and just go through what I'm going to use. Firstly, we have this partial matching, which is a partition into like sets A, Q, and K. But the important thing is that really the Q and K comes as like a some pairwise elements with pairwise cells with phase relation in between. And what we are really, or if we are like being really sticking close to the intuition, we are like just introducing a lot of arrows on the simplicial complex. So here, like alpha 1 is like being mapped to beta 2, and gamma 3 is being mapped to beta 1. So we have a lot of arrows here. And then we have gradient paths, which essentially chains up all the arrows. Which allows you to essentially allow a cell to like walk on the arrows to reach other places. And in this image at the bottom, the significant gradient path is when you walk from this gray edge, from the gray edge, which is beta 3, and then you can like walk along it and you go to gamma 1. You go to gamma 1 maps it to beta 2, and you look at another phase of beta 2, which is gamma 3, and you go along, you go to beta 1, and then you go to gamma 2. So that's like a gradient path. And a Morse complex, is the complex you get when you do this reduction, and the way you do it is like you stretch your edges in the previous case, the beta 3, all the way along to all the way along the different like we stretch it all the way along the different different gradient paths, and then we get a Morse complex, which have the same homology as the original complex, but with a lot fewer cells. So how does this idea apply to to our filtration? Turns out that what we want to do is we want to construct an acyclic partial matching on every frame of, like we start with a filtration. What we want to do is like we construct an acyclic partial matching at every frame of the filtration. And importantly, we want there to be some strict relation between the three partitions. So A, which I forgot to mention, are the critical cells, which were also the cells that are going to be stretched along the gradient paths. And then K and Q are the non-critical cells, and we want there to be some strict some strict subset relation between the three partitions at each frame. And importantly, for this like WP, so the W function, which is like the matching function, will end up going to we end up having like the same matching function for the entire filtration, just like depending on restriction. And the important implication of this like having the same matching is that if you have two cells that are being matched, so one in K and one in Q that are being matched, they all have to belong to the same, they either belong to the same frame or they do not belong to the same frame. So you cannot have a non-critical, so you cannot have like a pair of non-critical cells that are being matched, but they but the first frame they are born is like the first frame they exist cannot be different. They have to like come into existence in the same frame. So that's like the acyclic part, uh, and uh, and you may already be able to guess what is going to happen, which is the main theorem of this reduction. But which is okay, I will just show the theorem first. So turns out that if you look at like all the individual Morse complexes, so the Morse complex is like just like it's basically the critical cell with like a given boundary, like with like a highly modified, I would say, highly modified boundary incidence function. So if you look at the Morse complex of each frame, so AP, and then you look at the B prime, turns out they also becomes like a filtration, uh, and uh, and and in fact they have the same and in fact they have the same persistent homology groups, same persistent homology groups as the original filtration, which is a theorem given by Miss Chaikal and Nanda. So and so if so so turns out like this construction of Morse filtration is this construction of Morse complex really generalized to the entire filtration. So you just if you use the discrete Morse theory reduction on every individual frame, well, everything fits together really well. So for example, like for for example, one subtle feature is that when you have a filtration, your boundary incidence function has to be the same all along every frame. Same in the sense that you have the restriction. And when you look at the Morse filtration, that's also like that feature also exists where you can like use a single modified boundary incidence function for the entire Morse filtration. And and just to like I guess to because it's relevant, the way this one important reason this uh relation holds, I mean you can treat it as an interesting fact that is useful for proving the theorem, which is if you have a so if you look at the gradient paths, remember the gradient paths. So we are not discussing it here, but we discussed that as we discussed last time. The gradient paths are important to the construction of the Morse complex. So if you have a gradient path, say, and then you have a gradient path row in the P prime, in the P prime frame. So if you have a certain, now you look at you look at a critical cell alpha at the P frame at the P frame. So alpha is a critical cell because it's like if the first cell, because it's a first cell of the gradient path. So if the first cell of the gradient path is in a certain P frame, where P is less than P prime, then the entire gradient path is actually at the lower, is actually will be at a lower frame. And the reason this is significant is that it, in a sense, the gradient path also respects the filtration really well. You just need to look at the first cell of the gradient path, and you can and you can and you and then the gradient path will behave nicely. So okay, so this is a bit out of place, but this is like I feel like if you think about the Morse complex as stretching along the gradient path, I hope that offers some insight why the entire construction just comes together. So and so that's more or less what I want to say in the terms of like reducing precision homology with discrete Morse theory. And I figure, well, that's I figure that's like a relatively short talk. So I feel like, oh, that it's probably good for me to just add a few more some ideas that are highly related to what we are talking about today. So the first is regarding computing the precision homology. Like that would hopefully also share some insight why the reduction is considered an efficient way. So when you compute the homology of a when you compute homology, what you do in what you tell the computer to help you to do is so this is you construct a function, you construct a matrix, which is the D boundary matrix, and you make the columns the input to each you make each column to represent an element of a basis of the D cell, and then basically you make each column represent a D cell, and then you make each row to represent a D minus one cell. Then you construct the matrix using the you construct the diff differential like of the chain map, and then you represent it using this matrix. Then you do some reduction on this matrix, and then like with certain technique, you fit together like the number and you get the homology. And the expensive part about when you have like some really huge cell complex, the expensive part is really reducing this matrix. And this goes to why this persistent. So just looking at this, you can already see why we want why reducing the number of cells is interesting. But I think a bit more interesting, which goes to why the persistent homology is computable, is that if we look at this this differential slightly differently, in the sense that we arrange because we were talking about filtrations, right? So we have like a lot of simplicial complex or a lot of cell complex to fit into our framework. Then what we can do is like we can order the elements. So if a certain D cell it first appear in the first frame, then we group it in the first. And if some D cell, if they first appear in the second frame, then we look at it in the put it like after the cells in the first frame, and we do the same for the first frame as well. So if we look at this submatrix, this is really partial D of the second frame. So this is the partial D of second frame, and we can like really do this part and then we increase it all the way, and then at the end we have like the entire partial D of the entire filtration, which we use x to represent here. And turns out, and this goes to why this persistent homology method works at all. Turns out because this differential partial D generally speaking, a really sparse matrix. So if we like be careful with the kind of linear operations we do on this matrix, we can respect this framing, like we can respect this division into different frames and still compute the homology. And for that reason, if we look at the, if we look at the, and that is also being respected by the Morse filtration. So for that reason, I think, so, so yeah, and that's the basic idea of why persistent homology works. Like even though we are like talking about, oh, we are going to look at many different values of R, but turns out if we arrange them the right way, it's like the same as computing the homology for the largest simplicial complex. Okay, so this is like the first related topic that I want to discuss. And then the second related topic, which I figure would be interesting to talk about, is how persistent homology is related to not discrete Morse theory. Because that's I also so because there is actually an as we said earlier, discrete Morse theory is inspired by the smooth Morse theory. And we use that to introduce a way to reduce the computation of persistent homology. But turns out there's like another really natural way for the Morse theory to be incorporated into like this idea of persistent homology that is not really related to discrete Morse theory. And I figured it's probably good. I figure it's good for me to like briefly mention it in case you realize. So in case you're interested in it, and then sometimes you see different versions of the Morse theory and you are confused. Right? So the way to look at this idea, so the basic gist of this idea is that if we look at like this huge complex at the end, we can imagine that we can actually assign to each simplex of this, we can assign each simplex a value of the R, or a value epsilon, which is when the simplex first occur. So I'm going to like just write out this. So like we have like VS torus Rips complex here as we previously defined. Then we can define this function, which is from the union of all VS torus Rips complex. And remember, because the if when we have like really huge radius, or every vertex is like well connected. So what we actually get for the VS torus Rips complex at the end is just a single simplex, which have every vertex where every element of X is like its vertex, right? So, and we have a function mapping these simplexes to R, and the value is defined to be the R star, which is the first VS torus Rips complex they occur. So for all R greater than R, so alpha is in the R star VS torus Rips complex, but it is not in any VS torus Rips complex VRR. That's where R is like greater than R star. And I should note this is like another like small discrepancy that I didn't mention earlier. You may notice that when I draw the filtration earlier, I was like using the P frame, P plus one frame, P minus one frame. That means like that means I have like discrete frames. But when I'm looking at the different radius, I'm looking at like some continuously changing radius. And the reason we are allowed to do that is that only finitely many, like the VS torus Rift complex, it really only change finite if, like, assuming if we have like finitely many vertices to begin with, the VS torus Rift complex, it really only changes finitely many times as we increase the radius from 0 to infinity. Like if we hit the
Can I ask a question? So I'm
yes.
confused. Maybe I'm misunderstanding this. So alpha is in here VR star. But R star, so this is the R star is the first radius where this alpha appears, and then right,
Yes.
and then R is
Yeah.
greater than R star. But isn't that the case? The alpha is going to stay in the
Oh yeah, yeah. So, I'm sorry. Yes, yeah. Okay.
Okay. That
No,
was a
thanks for pointing out the mistake. It should be R small. Yeah, yeah. That's a huge mistake. I'm really sorry. Uh, yeah, that's a huge mistake. Yeah, but this is yeah, yes, thank you for pointing out for me for yeah, that's a mistake, important mistake. uh and that yeah, yeah, yeah. And because the simplicial complex is only going to change finitely many times, we can really look at the different frames like finitely many times. And yeah, and that, so in case that's a problem that came to you, um then that's the reason, like, instead of using a continuously changing radius, we can really look at the filtration in the terms of discrete frames. um and and the reason this is, yeah, and then the reason this is related to the Morse theory is that because in Morse theory, a very important idea is called the sublevel set, and in this case we can like also call it the level subcomplex, which is we define the function f at the beginning, then we can look at the f inverse from 0 to R, which then that would be, yeah, that just means all the cells in the delta X where F alpha is less than or equal to R. And if we, and then this sublevel complex is actually precisely the Weier's torus Rift complex. And because like sublevel set is like something that that is like being studied extensively in both discrete Morse theory and smooth Morse theory, that's why there's like this inherent that's why there's this inherent relation between the Morse theory and the persistent homology that is actually different from like what I have been talking about all along. And this is as far as I'm going to tell, but this is also an active research area. So if you are interested, so I figure it's good to mention it because, well, like, you, in a sense, you have like two marriage between the Morse theory and the persistent homology, but they are actually quite different. So yeah, and this is the end of my talk. So thank you everyone for joining. So if you have any questions, I'm happy to answer.
Okay, thank you, Chung-Ping. Yes, any questions?
Thank you.
Okay. I have one question. So I'm a bit confused by this but the lemma that you mentioned. I think we can always find a when you have a filtration and a gradient flow that's compatible with the filtration.
Yeah.
So you show
Yes.
you can always
Yeah.
restrict to a certain smaller dimension. So is it the case that you can choose the flow in that way, or is it that any flow, I think you gave a definition that being compatible with the filtration is going to
Okay.
automatically by this?
Okay. I think Aziz want to ask question, but I will answer the question of Cihan first. So the important
Do you hear me now?
the importance of like the idea of this lemma is that
Okay,
it
sorry,
depends
I
on.
checked.
Yeah, I think Aziz is lagging, but yeah, I will quickly answer Cihan's question first. So the idea of this lemma is that it depends on where alpha starts, basically. Like it depends on where the first cell of the gradient path occurs. So it means like if you have if you choose a cell like so the first cell of a gradient path is always going to be a critical cell. And depending on where the critical cell is, you don't have to it basically says, okay, what it really says is that in order to change like the phase boundary incident, in order to manipulate the gradient paths that originate from this critical cell, you don't have to look for cells in frames in the later frames. It means like if p prime is like greater than p, then like the frames happen later. So if you are changing this cell, you don't have to like look at all the frames that comes after it. So that's the idea of this lemma. So and
Okay.
which is really just really technical, a really technical part of the proof. That's why, but I feel like I guess that's like an interesting enough fact that that would be that I hope it's that shines a bit more light on this filtration structure. So
Is this connected to the fact that when you apply Morse theory to these so when you apply the Morse theory to the filtered complex, you get a filtered Morse complexes, right? So
yeah, it is related. Yeah, it is related.
Is that property coming from this lemma, or is it not related in that way?
I mean, this lemma is part of the proving the
Right.
entire thing. Yeah, it is part of the proving because ultimately, the difficulty of this theorem, lies in the fact like in proving this theorem lies in the fact that like you want everything to like fit together, and that the fact that yeah when you manipulate a gradient flow, you don't have to look at simplexes that come after it. Is like part of why it's important in proving, like in controlling what can happen and what cannot happen when the theorem expands. So like when you are like cutting down the cutting down the cell complex, or in this case the filtration. So
Okay. I see Aziz is back. Maybe Aziz, you want to ask your question now? Okay, maybe not.
No. I'm here.
Okay.
Yeah, I am here. Sorry. No. I
yeah.
just want if he can tell us what kind of okay, we know they use it in statics and things, but what other things they use this kind of homology? Do you know, or you have an
The
idea?
persistent do you mean the persistent homology?
Yeah.
I think this and okay, so the reason this persistent homology thing is like have a lot of interest is I should say this barcode thing. That's so the barcode is yeah, I'm glad you asked this question because then I get more opportunity to explain this persistent homology. The main so the the main usage of persistent homology is mostly in applied scenarios, and people really like to use it for neuroscience, etc. I think neuroscience is like uh, a huge application of this like persistent homology. So this barcode and this persistent homology groups like for different p and p prime and different dimension D. Like these two are equivalent formulations of the persistent homology. But the formulation of persistent homology that actually see the most usage right now is the persistent diagram. Well, so they all are equivalent. But importantly, when you
But
yes,
it's only like for big, what I understand, like to understand some big data, right? To study some big data, right? They're using it.
No, they don't use it to study a big data. The interesting part about this barcode is that turns out that you can construct a single pseudo metric space to contain every possible barcode. Like if you're asking why people care about this persistent homology, the reason is turns out you can construct a single pseudo metric space to contain every possible barcode ever. That means you can really compare a lot of different barcodes that come from completely different applied scenarios. And that's like if you want to ask why people care about this persistent homology, that is perhaps the most important reason. So, but I think I'm not getting your question. Can you ask it clear?
No,
Can you
it's
ask
okay.
again and see? I think I'm probably
No, it's
misunderstanding.
okay. You answered it. It's okay. I was thinking something else. Yeah, okay.